All right, this video is from Chapter 4, Section 1, and our topic is angles and their measures. What you're going to learn about in this lesson is what's called the problem of angular measure. We're going to talk about degrees and radians, circular arc length, and we'll look at angular and linear motion. And why we're learning about this, angles are the domain elements of the trigonometric functions. So why 360 degrees? Well, here we have a right triangle, and the Greek letter theta is going to be our variable, our angle variable. Okay, so you're going to see theta a lot. And here we have a hypotenuse in the side of a right triangle. Theta is a central angle intercepting a circular arc of length A. So over here in the picture on the right, we see, if you envision a circle all the way around here, what this says is that this part of the circle here, represented with the letter A, is a circular arc of length A. So arcs have length. It's a portion of the circumference of the circle. And that arc has an angle that's associated with it, and we call that a central angle. So the measure can be in degrees. A circle measures 360 degrees once around, we know that, or in radians. So we can talk about the radian measure of an angle, which measures the length of arc A. So just to put a quick application on angle measure, a lot of times we use angle measures in navigation, and we talk about the course or bearing of an object, which is sometimes given as the angle of the line of travel measured clockwise from due north. So here I have three examples, and in the first one you can see due north would be, if we were drawing this on our page, would be a vertical line on our page, and a 90-degree angle from due north would be due east, so that's 90 degrees, and the bearing is east 90 degrees. And then here we have the next example, which would be south, which would be 180 degrees. So the bearing of south is 180 degrees. Southeast, okay, if this is east and this is due south, 45-degree angles, a 45-degree angle from east would be southeast, halfway between east and south, and that would be a total of 135 degrees. So let's talk about a radian. This is a new unit of measure for us. So a central angle of a circle has measure 1 radian if it intercepts an arc with the same length as its radius. So if we have a circle, and this line here would represent the radius of the circle, and if the length of that radius is the same as the length of this arc, then this angle is said to have had a measure of 1 radian. All right? So if the arc length is less than the radius of the circle, then this angle is going to have a measure that's less than 1 radian. And if this arc were greater than the radius of the circle, then this angle would have a measure greater than 1 radian. But a radian is defined this way. So one of the things that we need to be able to do is we need to be able to convert degrees to radians and radians to degrees. And so anytime we're asked to convert one type of unit to another, we're going to be using conversion factors. So here are our conversion factors to transfer units. Angles to radians, radians to angles. Okay? So 180 degrees, halfway around a circle, we call that pi radians. Okay, so 180 degrees equals pi radians. So if we're converting radians to degrees, then we're going to multiply our radians by 180 degrees over pi radians. And if we're converting degrees to radians, we're going to multiply by pi radians over 180 degrees. So for every 180 degrees, there are pi radians, and for every pi radians, there are 180 degrees. So applying this, how many radians are in 135 degrees? So example A. Example B, how many degrees are in 7 pi over 6 radians? And example C here, find the length of an arc intercepted by a central angle of 1/4 radian in a circle of radius 3 inches. So pause the video right now and go ahead and try these 3 examples. And when you're ready, play the video and we'll take a look at the solutions. So the solution for A, how many radians are in 135 degrees? So we're converting degrees to radians. So we're going to use our conversion factor of pi radians over 180 degrees. Okay, so here's the setup. Now, how we know that this is the way we're setting it up with the conversion factor, remember, when we multiply here, what we want to have happen is we want to have the units cancel. So we need to have units in a numerator and units in a denominator in order for those units to cancel. So that's how we know that we need to set the conversion factor up this way. So when we multiply this, we get 135 pi over 180 radians, and we can simplify that fraction, so this reduces down to 3 pi over 4 radians. So a 135 degree angle is equivalent to 3 pi over 4 radians. Now converting radians to degrees, we're going to use our conversion factor 180 degrees over pi radians. Again, here's the setup with the conversion factor. We have radians and pi in the numerator here and here in the denominator of our conversion factor. So when we multiply, those units are going to cancel. So we have 7 times 180 over 6, which is 1,1260 divided by 6, which is 210 degrees. So 7 pi over 6 radian angle is equivalent to a 210 degree angle. Find the length of an arc intercepted by a central angle of 1/4 radian in a circle of radius 3. Well, a central angle of 1 radian intercepts an arc length of 1 radius. So in this case, it's 3 inches. So a central angle of 1/4 radian intercepts an arc of length 1/4 radius, which is 3/4. And if you remember, our definition was 1 radian, the radius and the arc length were equal to each other. So here we have the angle being 1/4 of 1, so the arc is going to be 1/4 of the radius, which is given to be 3. So 1/4 of 3 is 3/4. So here's a formula for measuring arc length in radian measure. If theta is a central angle in a circle of radius r, and if theta is measured in radians, then the length s of the intercepted arc is given by s equals r theta. Fairly simple formula. In degree mode, if theta is a central angle in a circle of radius r, and if theta is measured in degrees, then the length s of the intercepted arc is given by s equals pi r theta over 180. And all this is just taking the conversion factor pi over 180 and introducing it into the radian formula. So let's apply this. Find the perimeter of a 30-degree slice of a large 8-inch radius pizza. All right, so go ahead and, so here we got a slice of pizza. We want to find its perimeter. We're told that this is 30 degrees and the radius is 8 inches. So find the perimeter of that. So we have 2 sides. We just need to know what the measure of that arc is. So go ahead and calculate that, and we'll take a look at the solution. So let S equal the arc length of the pizza's curved edge. So we have degrees, so we're going to convert using our degree arc length formula. So S equals pi times 8, the radius, times 30, the angle measure, all that over 180. So we get 240 pi over 180, which is approximately 4.2 inches, and we'll go ahead and convert this to a decimal approximation. We could leave this in terms of pi. So P equals 8 inches plus 8 inches plus whatever our arc length is, which we just found to be 4.2. So the perimeter of that piece of pizza is 20.2 inches. Okay, so some applications of angles and arc length. Angular speed is measured in units like revolutions per minute. Linear speed is measured in units like miles per hour. How fast a tire is spinning, for instance, is measured in units like revolutions per minute. Linear speed, like how fast your car is driving on a road, is measured in units like miles per hour. So there's a difference between the type of motion that we're looking at, angular versus linear motion. And one application of this is is what's called a nautical mile. And maybe you've heard of a nautical mile before, maybe you haven't, but a lot of times ships use nautical miles, and because they're traveling on the ocean, sometimes it's very difficult to measure straight line, miles like we're used to thinking of linear miles. So a nautical mile is defined to be the length of 1 minute of arc along Earth's equator. So basically what this is saying is that a nautical mile isn't the straight distance from point A to point B on the Earth's surface. It's actually the length of an arc, because the Earth we know to be round. So the distance from point A to point B on the Earth is actually a curve, the length of a curve. Okay, which is actually pretty interesting if you think about it. And in geometry we study lines and angles and things most of the time in 2 dimensions, sometimes 3 dimensions. The geometry that we study in high school is what's called Euclidean geometry, planar geometry. This concept of a nautical mile is just a very brief introduction to a concept called spherical geometry. There's a whole nother type of geometry where lines are not lines that we think of, the straight distance between point A and point B, they're curves. And it's actually very interesting.